Hi, and welcome back. I'm Rob Shapiri. I'm a professor of computer science here at Princeton, and we are extremely honored to have Barbara Liskov as our next speaker. Barbara Liskov was born in California and received her bachelor's from Berkeley in 1961. She spent a year at MITRE and a year at Harvard before returning to graduate school, where she received her PhD in 1968 from Stanford. She actually started out working in artificial intelligence. Her advisor was John McCarthy, and she wrote a thesis on playing chess. After graduation, she went back to MITRE for several years, and then in 1972, she joined the faculty at MIT, where she's been ever since. At MIT, she created two early programming languages, which were the forerunners of modern object-oriented languages like Java. She later worked on distributed systems with research on a broad range of central issues, including the design of reliable, fault-tolerant systems. At MIT, she was named the Institute Professor in 2008, MIT's highest faculty honor, and she is also the Associate Provost for Faculty Equity. Her awards and honors are too numerous to list, but to name just a few, she is a member of the National Academy of Engineering, the American Academy of the Arts and Sciences, Fellow of the ACM. In 2004, she won the IEEE von Neumann Medal. 2005, she won an honorary doctorate from ETH. And in 2008, she won the Turing Award, quote, for contributions to practical and theoretical foundations of programming language and system design, especially related to data abstraction, fault tolerance, and distributed computing. So please welcome Barbara Liskov.
Thank you very much, and it's a great honor to be here. I need to figure out how I'm going to use everything. All right. So when I got started in computer science, I was building on the shoulders of the people who came before and just took for granted that there were universal machines. Of course, as we heard this morning, they weren't exactly universal, they were approximations to universal machines. And I was just one of those many people who saw the opportunity at that point in time of a great new field that was opening up. I do have a kind of a funny story related to Martin Davis's talk this morning. Right after I got my PhD, one of the projects I worked on was a project to produce a sort of general instruction set or sort of a more conventional instruction set out of a RISC instruction set using microprogramming. And I think it's kind of funny the way that instruction sets have varied over the course of our field, where for a while RISC was very popular, then it went back to a more general instruction set. As you absolutely are correct, you know, it doesn't really matter what that instruction set is, except that if people have to write the programs in very tiny increments, it gets very tedious. Fortunately, nowadays we have compilers and they generate the code for us, and so in some sense it really doesn't matter what's down there. Anyway, what I'm going to talk about today is the problem that I confronted, which is whether you have a very simple instruction set like Turing proposed, or a more complicated one the way that von Neumann proposed, neither one of them gives you very much guidance about how to build the huge software systems that people are actually building. And in spite of the very optimistic message that you heard yesterday, which kind of implied that just by magic these more and more powerful software systems are coming into existence, the truth is it's not easy to produce those systems. And there's been a long period of learning how you organize software so that you can actually end up with the systems that we're interested in producing. So that's what I'm going to talk about today. I'm going to talk about the problems of software and how we came to realize what we should do about them. So the problem is software is very complicated. The systems are huge. There are millions of lines of code. And they do very complicated things. And you heard, very interesting discussion last night about the very complicated things they do. And furthermore, they might be distributed, they might be concurrent, and that just makes it more difficult. And the problem that I got interested in early in my career was what can we do about this? Now, one way in which we've made tremendous progress since when I started out was that we understand so much more about how to approach a lot of the problems that we have to solve in software systems. So we know a lot about very efficient data structures, very efficient algorithms, complicated but well understood protocols. You'll hear Ron Rivest later today talking about how we do encryption over the internet. And these are tools in our toolbox that we just know are there. And so we don't have to think about these as hard problems to be solved. We have these tools available to us. But that doesn't get to the real crux of the problem, which is how do you actually organize the program in the first place? And that's the problem I got interested in around about 1970. And it's related to two fields of research in computer science: programming methodology, which has to do with how do you organize, how do you think about software, what are the ways that you think about organizing. And then a related field, in my mind, programming languages, because once we understand how we should be doing things, we can often move those ideas into a programming language and make it easier for people to use the ideas when they develop software. So what I'm going to do in my talk today is I'm going to start by talking about programming methodology, and then I'll move into talking about programming languages. And I'll end up with a few remarks about where we are with programming languages today, sort of idiosyncratic remarks representing my position. Okay. All right. So here's the situation in 1970 when I started working on this problem. There was something called the software crisis. And people were really very concerned about this. What this meant was we had no idea how to build the software systems that we wanted to build. Now, I was working at MITRE at the time, and MITRE is a company that does a lot of development for the government. And the government was very concerned with this problem, the US government, because they had in mind very complicated systems that they want to build, missile guidance systems and stuff like that. And they understood that they really did not know how to produce that software. And so they asked MITRE to look into what are techniques that we can use so that in the end, we can produce software that does what we want to do. And I was given this as a project to work on. That's how I got into programming methodology. And just to finish up some more stuff about the software crisis, it was exacerbated by the fact that hardware was very expensive. And so typically when there was a project that people were starting to get ready for, they would undersupply the hardware. They didn't really understand the cost of developing software. But there was a kind of naive idea that the software can take care of the problem. But of course, that just made the software problem harder because it meant you had to think about how to cram something that maybe would have been a little easier if you'd had a large amount of memory. And of course, these are all approximations of universal machines, so they don't have infinite memory. They have some, at that point in time, pretty limited amounts. I think the machine I was working on at that point had 32K words, maybe it was 16K words, I mean very small by today's standards. So people were trying to build big complicated systems on small amounts of memory. The other thing I wanted to mention was that the software crisis was pervasive throughout the 70s and the 80s. And it was very common to see newspaper stories about Project X, where they had spent millions of dollars trying to develop a system to do something or other. These systems weren't doing anything as complicated as the systems we build today. And then the whole thing would fail. They'd have to just abandon the entire project. So it was a really big, important problem. Now, this was a totally new field to me because, as was mentioned in the introduction, I did my thesis in AI. And I was switching into the systems area when I went to MITRE. And then I was handed this problem in programming methodology. So, of course, I did what you do when you start to develop a new field. And in a way, I'm picking up on the kinds of talks we've heard throughout the conference, but I'm talking about a different generation. So I'm going to tell you a little bit about the literature that existed about programming methodology at that time. I was informed that the screen would go black, but I could just touch it and it would come back, but that doesn't seem to be true. Anyway, so where was I? Oh, so I was saying I was looking at the literature. I'm going to tell you about some of these very interesting papers, and you've heard some of these names already today because I have a paper here by Dijkstra and later on a paper by Hoare and also a paper by Weert. Okay. So before I get started, I just want to mention that programming methodology is actually about two different but related topics. I see, right there is where I have to touch. All right. And the first one is about design. How do you design a program so that in the end it will do what you're supposed to do? And one thing I wanted to mention to you, by the way, is that at the time I was doing this work, I kind of envied electrical engineers. And the reason I envied electrical engineers is because even though we only had 32K of memory, but of course we had tapes and stuff like that, there was absolutely no structure superimposed on a computer program. And so you could just do anything. It was infinitely plastic. Whereas I felt the engineers, they had to work with components, connect them by wires. And this forced a certain kind of discipline on the process of organizing things that was totally lacking in the software world. So program methodology was about how do you design programs, and they used to talk about programs that were correct by construction. This was a goal, that you could just build your program and it would work. I don't mean this in the trivial sense of you write a program, it doesn't have any bugs in it from day one, but I mean the basic structure's right, and then with reasonable amount of debugging and testing, in the end you end up with something that at least works most of the time. I mean, even today, programs don't work all the time. And then the other question, which is related but not exactly the same, is what is the structure of programs anyway? And I mentioned before that, and the electrical engineers had to connect things by wires, and there was no such notion for software. But in fact, we needed a notion like that. Okay, so here's the first paper. I'm only talking about a few papers. These are papers I read at the time. This one, the paper by Eggster and Dijkstra on go-to statement considered harmful, just because it's extremely interesting. And it's interesting both in what it says and also in what it says about the time. Okay, so the paper is the go-to statement considered harmful. It's not even a paper, it's just a couple of page letter to the communications of the ACM. And in it, Dijkstra said something that to us seems totally obvious, because all programming languages today do not have go-to statements in it. But at that time, of course, they did. And the statement was very controversial. He said, you should not use go-tos in building your programs. And the reason he gave an analogy to explain his reasoning. His analogy was, if you're debugging a program and you're at a particular place in the control flow and you know there's an error there, in order to understand what happened, you have to know how you got to where you are. And if you have a program with go-tos, it's arbitrarily difficult to figure that out. But if you have a program that's well structured, it has for loops and ifs and recursion and so forth, then it's relatively easy to figure that out. And so he said that's why go-tos are bad, because programs are inherently difficult to reason about. When you reason about a program, you're looking at a static thing, the program text, trying to understand a dynamic thing, which is what happens when the program runs. And in order to make this job as simple as possible, we should try to keep the structure as good as we can, and go-tos interfere with that. Now, the reason this was so controversial, there were really two reasons. One was people were insulted. So they said, I use go-tos and I write very good programs. And in fact, that's true. Because if you're well disciplined, if you pay attention to what you're doing, you can write a good program no matter how terrible the programming language is. And so you can use go-tos in a way that sort of simulate well-structured programs. The other reason was I think people were really worried about expressive power. The programming languages at the time had go-tos, and they were lacking certain kinds of features that we think are important today. They didn't have exception mechanisms, they didn't have case statements, and people were really worried that without a go-to, they might not be able to build efficient programs to do what they needed to do. Okay, so that's the first of the three that I'm going to talk about now. The second one is a paper by Nicholas Weert. This is about a different topic. This is about program design. And what Weert is proposing here is top-down design. We understand today that top-down design is the way that you should design programs, but your process can't be entirely top-down. Top-down means you start with the idea of what it is you're trying to accomplish, and then you develop the program structure always having that in mind. So you work from the problem you're trying to solve down to the program structure that realizes it. What Weert did in this paper was he took the 8 queens problem, which is, as you know, the one where you try to get queens on 8 columns in a way that none of them is attacking any of the other queens. And he proposed that you develop a program by making one design decision at a time. And his first design decision for this was that he's going to attack the problem column by column. So he's going to imagine that he has a solution that works for n columns, and then he's going to try and extend the solution to the n plus first column by adding a queen to that column. And if that still satisfies the constraints of no attacks, then fine, he can go forward till he has all 8 columns, or in fact, you can see this could go for an infinite number of columns and rows. But if not, he'd backtrack. And then what he said was, well, the way you go from there is you write what he referred to as an abstract program, which is kind of a little program written as comments that enshrines this idea about how you're going to develop that program. And then you take some parts of that program and you refine them again by making a second design decision. So that was his basic idea. Okay, here's the third paper. And this is the one I think is the really important one. This is Dave Parnas's paper. Dave actually wrote 2 papers at about the same time. And this is a paper about program structure. So it is getting to the heart of this question about how do I organize programs so that in the end I'll be able to sort of put them back together again and think about them. And what Dave said in this paper is quite revealing, because he began by saying programs are made up of modules, but I don't know what these modules are. But nevertheless, whatever they are, we need to understand how they're connected together. And the notion of connection has to be very complete. So he said, this is a quote from his paper, the connections between modules are the assumptions which the modules make about each other. So he's saying it's not so simple that you just have module X which calls module Y. They might have other ways of communicating, and you need to understand thoroughly all the ways in which they communicate, otherwise you won't be able to think about them modularly. Okay, so what is this idea of modularity? Because this turned out to be the critical thing that was developed in programming methodology at this period in time. So program's collection of modules. At this time, people didn't know what modules were, but they knew they were aiming for it. And I can remember, I don't remember what papers these were, but I can remember people saying things like, oh, module shouldn't be bigger than 1,000 lines of code. Maybe there was an idea that you just break your program up into 1,000-line chunks, but of course that's not really going to work. People didn't know what these modules were or how to get them, but they knew they were aiming for something called modules. And then they knew that what you'd like to do is to define an interface for a module. You'd like the module to be a black box, and you'd like to have an interface for the module that you describe completely by what we call today a specification. I don't remember when that terminology came into existence. And this is exactly what Dave Parnas was talking about in his paper. He was talking about what has to go into that specification. Okay, now if we can do that, then we have modularity. We have modular or local reasoning. Because what we can do is we can reason about the correctness of an implementation of the module by just asking the question, does the module meet its specification? And we can do that without having to think about the rest of the program. So if you think about a module, it doesn't matter exactly what size it is, but it's going to be small compared to the gigantic million lines of code that you have in your whole system. If you can reason about that little module independent of the rest of the program, that's a huge win. And then, of course, the using module, to make this work, has to, in fact, the specification has to be complete. The using module has to depend just on the specification and not on anything else, otherwise it's going to interfere with this. And just to give you an example, a very simple one, a procedure is a very nice kind of module. And the sort routine is a very nice example of what a module is. We know that what we rely on this sort routine to do, we give it an array as an argument, and when it gets returns, that array has been sorted into sorted order. And that's what we rely on when we call the sort routine. And we don't care what sort algorithm is being used inside that sort routine. So we get this kind of modularity where we could reason about the correctness of sort just by knowing that it has to satisfy that specification. And when we use it, we don't think about the implementation, we just rely on the specification. So the situation in 1970, procedures was it. That's all we understood. And they're just not powerful enough. I mean, a file system is a very useful module. A database system is a very useful module. I mean, I'm talking from today's perspective, although people knew about file systems then. They're not procedures. You know, they're something else. And furthermore, procedures were not used as much as you might have thought. And actually, when you think about Wirt's methodology, you can almost see they weren't going to be used, because Wirt was thinking about a program that just got sort of more and more elaborated. And you might have a procedure here and there, but they were not a major building block in building that code. And the programming languages at the time sort of bought into this, because if you think about ALGOL 60, which was a very influential language and a very important language, okay, it has that idea of block structure. And block structure, the idea is, you get down into inner blocks and you have a little protection of what's going on in the inner block, but it's not a procedure. It's just, sort of smaller and smaller stuff. And in fact, it encourages something that's really bad, which is communication through global variables. So an inner block had local variables, and outside you couldn't see them. So that was good. That was a kind of modularity idea. But the outer block had variables, and everybody was free to use them. And so there was a lot of communication going on that sort of wasn't easy to capture. Okay, so that's the situation in 1970. And what happened was, I read these papers, a whole bunch of others, very good papers in the literature at that time. This is just a small sampling. And I realized that I had invented a methodology. And I had done this because I was developing an operating system, and I was worried about whether my group, my small team that was working on this, would actually be able to produce a working system in the time available. And so I decided that communication through global variables was a bad idea. And what I did was I broke it up. So the idea that I explained in this paper was this. I said, the system's going to consist of what I called partitions. Each partition has some piece of state inside it. There is no global state at all. The state has been entirely partitioned among these things I called partitions. And the rest of the program can only get at that state by interacting through this partition by calling its operations. So there were two ideas in here. There was this notion of encapsulation. There was no global state. It was all broken up. And then there was also this notion that the way you interact is through not just one procedure, but a bunch of operations. So I explained this in this paper. Now, it's 1972 at this point. I've been working in this area for a year and a half or 2 years. And at that point, I moved from MITRE to MIT. And this was a really serendipitous thing for me, because I had discovered the problem I really wanted to work on. And I wouldn't have been happy working at MITRE and then being asked to switch to the next RFP, request for proposals, and work on something else. I really wanted to put my own research ideas forward. So I moved to MIT in the fall of 1972, and what I was thinking about in that fall was, how can these ideas, my idea of partitions, Dave Parnas's notions about modularity, and some other things that were in the literature at that time, how can these ideas really be used in developing software structures? The problem I felt was that since people didn't know what modules were, at most they could give you sort of prescriptions. They could say a module's, 1,000 lines of code. A module's a partition with a few operations. And you could give an example. So you could say, here's a particular problem I developed. I used this structure in this particular way. And people would read these papers and they say, yeah, that looks like a good structure for that particular program. But when they tried to apply the ideas to some other program, it was sort of hopeless. And the reason was, it was a very nebulous idea. It didn't have anything you could get your teeth on. So people didn't know how to use these ideas in developing new programs. And I felt that it was because modules weren't really very well understood. They were pretty imprecise. What were they anyway? So I was thinking about this problem all the time. And sometime in the fall of 1972, or maybe it was the early 1973, I had one of those marvelous aha moments that few of us, I think, are lucky enough to have, where all of a sudden I saw that you could take this notion of a partition and you could rephrase it as a notion of a data type. And I knew when I had that idea that it was really important. And it was important for two reasons. One was, data types were something programmers knew about already. And you could see a path from here into a programming language. People write programs in programming languages, and that's their tool. And so here was a way I could get that idea into programming languages in a way that would really help people to move forward. The other reason, I think, is because a data abstraction is an abstraction, like a procedure is an abstraction. A procedure is an abstraction from the code that implements it to the behavior it provides. And I was able to get the same thing. Now there was a hope of getting the same thing in the data domain, and would be a much bigger structure, more like a file system or a database. For those of you who are students in the audience, I want to go back to something Eric said last night. He said he had no downtime, and then he said downtime is useful. I'm sure this idea came to me in the middle of the night. I mean, I really believe in downtime. And I find downtime to be the time that some of the best ideas come to you. A problem that seemed to be intractable the day before, when I think about it the next morning, I may all of a sudden have a glimmer of an idea about how to attack it. And it's downtime that does that. When you're not consciously working on things, you're unconsciously working on things, and that unconscious is a great source of inspiration. Okay, so there I am at MIT. That was my idea. I already said it. I connect. And you can see the connection. You know, the partition is an object. That state that's inside it is the representation of the object. And the operations used to interact with it are the operations of the object, you know. So it's like an array. An array was in all the programming languages at that time. It's a data abstraction. People use an array knowing that you can, you know, store into the array, you can fetch from the array. They don't worry about the data structures that are underneath to make that actually all work. Okay, so that was the great idea. In the spring of 1973, there was a very interesting SIGPlan SIGOPS interface meeting. This is a joint meeting of the Special Interest Group on Operating Systems, the Special Interest Group on Programming Languages, ostensibly about programming languages in which to program operating systems. A very boring topic. Boring because you can count the number of operating systems on the fingers of one hand, roughly, whereas there are thousands, hundreds of thousands of applications. And so programming languages ought to be focused on helping people build applications. There's a lot more bang for the buck. However, the meeting wasn't actually about this topic. It was about data abstraction, program methodology. That's what people were really interested in. And at that meeting, I started to work with Steve Zillis, who was a graduate student at MIT at the time and had some similar ideas. So Steve and I started to think about this notion of abstract data types and what it really meant. And in doing this, we were starting to move from program methodology into programming languages. We were quite well suited to do this as a pair because Steve came from IBM and knew all the IBM languages, and IBM was the dominant player in the commercial sector at that time. There was Fortran, PL1, COBOL. And I came from my AI background. I'd been using Lisp. We, of course, knew ALGOL. We knew most of the programming languages that were in existence at the time. The field was a lot smaller then. But we started to read the literature as well as, you know, trying to think about things. And so I want to mention again a few papers that were very influential. This is a paper about Simula 67, a very interesting programming language. Ole Johan Dahl and Tony Hoare described an early version of Simula 67 in this paper in this little black book, Structured Programming, a very interesting book with a paper by Dijkstra on top-down design, a paper by Tony Hoare on data representations. And Steve and I studied this paper carefully because Simula 67 was the place where inheritance came from. In Simula 67, there were classes and there were subclasses. And I will get back to this later. However, Simula 67 had no encapsulation. And at that time, I think it does now, but had no encapsulation. So there was nothing that prevented the program that was using these abstractions from actually reaching inside and mucking around with what was going on. And so we rejected it, partly because of the lack of encapsulation, but also because we did not think inheritance was such an important idea. Here's a really important paper, Jim Morris's paper. This is in the line of Parnas's paper. So Jim is thinking about modules. And what he's asking in this paper is, what is needed in order to get those benefits of modularity that I mentioned to you earlier? I think I mentioned them to you earlier, although I don't remember talking about them. So the benefits of modularity are, there's two of them. There's local reasoning, the ability to think about a module independent of all the code around it. There's also modifiability. You can, if you don't like the way your module is performing, the implementation you have right now, you can rip it out, replace it with something else, and if you did it right, the rest of the code is not going to be affected by the fact that you changed its implementation. These are very important properties. And what Jim was thinking about in this paper was, what rules do we have to enforce on how modules are used in order to make sure that we get these properties. And he pulled them out, the ones that seem obvious today. The first one was the code on the outside of the module had better not get in there and store into the variables inside the module that represent the state of whatever it is the module is implementing. I lost it again. Okay. And then he said, and furthermore, they really shouldn't even read those variables. Now, the modification is clear from the point of view of local reasoning. If you have code on the outside that can store into the modules on the inside, then how can I reason locally about what's going on in the module? I can't. The not reading has to do with the modifiability goal. If they can read what's inside, then you can't freely change that module. You would have to continue to satisfy their need to read the variables. So Jim picked up both of these properties, which in fact are the underpinning of modular program design today. And then he went on to say, well, how could we actually enforce this? And he didn't have any good idea about that. He said, well, we're going to use something called seal and unseal. And the way to think about this is encryption. So the module has a key. Every time it produces an object, it encrypts the object with that key. This means on the outside, you really can't muck around with the module. You can't see it. You can't modify it, because when it comes back in again, you can't see it because it's encrypted. If you tried to modify it, we'd know when you called one of those operations that it wasn't any longer in its proper state. But of course, if you had to implement this using encryption, it would be much too expensive for this to be a real solution. Okay, so then one more paper. I'm not going to spend much time on this, but this is a paper by Bill Wolf and Mary Shaw about global variables and why they're bad. I've really already talked about that. What's interesting, though, is that Bill and Mary were doing, at the same time I was developing CLUE, which I'll get to in a minute, they were developing a language called Alphard, which was the other major project in what is data abstraction. Okay, so Steve and I worked on this, and my memory of the summer of 1973 is that it was sunny all the time in Cambridge, Massachusetts, which of course it wasn't, because we used to meet for lunch outside in this lovely courtyard, and I remember us meeting for lunch every day. And that was our mode of operation. We'd meet for lunch, and then we'd separate and think about what we'd discussed and meet again the next day. And we produced this paper at the end of the summer in 1973. And what was in that paper was basically a proposal for what the notion of abstract data types actually are. And what it said was, an abstract data type is a set of operations and a set of objects. And the important point was that the operations provided the only way to use the objects. So if you wanted to interact with those objects, you had to call the operations. You couldn't go inside and muck around with them directly. The paper also proposed a sketch of a programming language that could be used to start to use abstract data types in writing programs. Okay, now after that paper, so now I'm in the fall of 1973, and I took the obvious next step of working on a programming language. And I'm going to give you some rationale for that in a minute, but I just wanted to mention these are the three students who, together with me, were the main developers of this language called CLUE. And the purpose of developing CLUE was to figure out what are these abstract data types really. Let's get a rigorous definition. This is a picture. This is me in 1974. I'm talking to Jack Dennis. Jack, who's a very well-known person in the parallel computing world, he's an advocate of data flow, was very interested in my putting concurrency into CLUE, but fortunately I didn't do that. All right, so why a programming language? It was the obvious next step, and you can see that the research was just marching around along in that direction, but there were some very good reasons for doing this. As I mentioned before, programming languages are the way programmers think about writing programs. So if there were a programming language that had abstract data types in them, then people could really use it. Another thing is we could figure out whether they really worked in practice, because if you have to write your program, so programming languages always take expressive power away from people because they hide the underlying machinery and present it to you in a more abstract way. And the proof is in the pudding. I mean, if you could write programs using abstract data types without having access to the internal mechanisms, that's a good proof of concept to show that the idea works in practice. Another virtue of the programming language is this way I was going to have a precise definition of what abstract data types actually were. And finally, I better find a way to implement them that provided reasonable performance. Now, Programmers in general are much too hung up with performance. So, I mean, all I wanted was reasonable performance, but if the performance was abysmal, this would be a showstopper. Okay, now what I'm going to do is I'm going to tell you a little bit about Clue, not very much, but just to give you some basic ideas. And here's some facts about it. So, first of all, it's a statically typed language. And not only that, but it's heap-based, and it supports separate compilation. And if you look at those three, what I see when I look at those three is I see my interaction with Lisp. Okay, so Lisp is a heap-based language, and Clue is just like Lisp. And of course, modern languages are all heap-based in the same way. You know, they're objects in the heap, you have pointers to them. And Lisp is a nice, separately compiled language. You just write more and more procedures, and your program grows. And Clue was like that. But Lisp is not a statically typed language. And so that was, I liked Lisp, but I did not like the fact that it wasn't statically typed because I found it very annoying that it didn't find errors, sort of obvious errors for me. So I wanted a statically typed language. And then, as I said before, I ruled out concurrency pretty early on. That was a really good decision. I went into this project saying, I'm just going to figure out what data types, abstract data types are. I'm not going to put anything extraneous into the language, because it was a hard enough problem as it was, and if I threw extra stuff in, it would make it just impossible. And I realized that concurrency would have been a distraction. I'm going to get back to concurrency later on. Okay, so Clue has a few mechanisms. I'm just focusing on abstraction mechanisms. I'm going to show you very high level a little bit about it. Okay, so a cluster, this is where the name Clue comes from. And the header of the cluster tells you what the operations are. And then inside the cluster, in the comments that are written in red, is the hidden stuff. Okay, so inside of here are some, there's information about how you represent those objects. Think about instance variables in Java. And then the operations are implemented, and they get to use those instance variables. But on the outside, you can't see any of this. All you get to do on the outside is call those operations. So it's a very direct representation of what I was talking about before. And it's all enforced through compile time checking. So there's no need for any seal and unseal, because the compiler knows if you're outside, you just don't have access to this stuff. It's hidden inside that syntactic unit. At the time, mind you, it was not so obvious how this was going to work, but that part turned out to be relatively easy to do. Okay, however, we didn't just want an int set. We wanted polymorphism, or generics as they're called today. We wanted to be able to define a general set which was parameterized by a type so that you could instantiate it, as I show you at the bottom of the slide, to get a set of integers or a set of reals or a set of strings or whatever kind of set you wanted, and then you could use it. Okay, and again, it has a hidden representation. It's only changed from what I showed you before in that there is a type parameter in the top line. Okay, this turned out to be much harder. And we knew going into this project that it was going to be hard. This is why we thought maybe we would end up having to use seal and unseal. But we really wanted a static solution to this problem. The problem is not every type, not every actual type makes sense as a parameter to a set of T. For sets per se, you need an equality relation. Okay, if it had been a sorted set, we would have needed some ordering relation. And a type that didn't have one of those things would not have been a legitimate parameter, and we needed a way of expressing that in a compile time, checkable manner. Otherwise, we would have had to resort to some kind of runtime checking. And it probably took us a couple of years to figure out a solution. This was our solution, what we called the where clause. So we added this to the header, and the where clause tells you what operations the parameter type has to have. Okay, once you have the where clause, you can do the separate compilation and static checking, because when you instantiate, when you provide an actual type, the compiler can check to see whether that type has the operations that are required. And then when you write the implementation of set, the compiler knows it's okay to call those operations because it's going to guarantee they're actually there when you get around to running. Okay? Of course, you notice that there's just syntax here. There's no semantics. And as I'm sure you all know, compile time type checking is basically a proof technique of a very limited sort. And this was about as far as we could push what you can get out of the static analysis. To go further where we would say, oh, but T in addition has to really be an equality relation, that requires much more sophisticated techniques that even today are really beyond the capabilities of a compiler. Okay. Iterators are kind of a nice story because I told you before, the screen is gone again. Okay. That I went into this project saying I'm only going to do what I need to do for abstract data types. I'm not going to put anything extra in the language. And iterators were an extra. We certainly did not foresee this when we went into it. It's clear many data types are collections. And when you collect things into a set, for example, it's because you want to do something with them later. So you're going to want for all and there exist, things like that, to do with your abstract data types. And the question was, how do you express this in a programming language? And we knew we really didn't need extra mechanism because there are two ways that you can do it without anything special. One thing is I could pull the elements of the set out one at a time, reducing the size of the set by one each time. That way I could iterate over the entire set. I'd know when I was done. But of course, in the process, I destroy the collection. And if you didn't want to destroy it, then you have this nasty little program you're writing where you're collecting the elements as you remove them and putting them back into some other set. Another thing you could do is you could complicate the abstraction. I could turn the set into a sorted set, and that way, or an index set, and that way I could sort of march through it index by index. But that's a more complicated abstraction, and from a programming methodology point of view, I don't like either of these solutions. The second is worse than the first because the second one requires that the developer, the program, complicate the abstractions, and abstractions really ought to be as simple as possible. So we weren't sure what to do with this, and I took my group of students to visit the group at CMU, Bill Wolf and Mary Shaw, and this was maybe in the summer of 1975, and they told us about this thing they'd engineered called generators. And generators think Java iterators. One of the things that's happened in the last 25 years is the names have all switched. So what I call polymorphic, they call generic. What I call iterator, they call generator. I think what I'm calling generator is today called iterator. So that's the way it was. So they had this notion of generators. They were sort of special objects. You would create one when you entered a loop. You would have an operation where you could pull the next element out, very much like what Java provides today. And so we could see this was a solution to our problem, but we thought it was sort of a nasty solution. It was inelegant. And on the airplane flying back to Cambridge, my student Russ Atkinson invented iterators. And iterators are a very simple notion. They are sort of fancy procedures. So here I'm showing you an iterator. It happens to be an operation of sets that will iterate through the set, giving you the members of the set one by one. When you start up the loop, you call the iterator. When it's ready to produce the next element, it yields it, and this causes the body of the loop to run. When the body of the loop is finished, control goes right back in the iterator at the point where it left off. And then when the iterator is finished, it returns and the for loop is over. So it's a very straightforward mechanism. What's nice about it compared to generators is that the stack holds your state. So when I'm inside the iterator and I've produced the next element, then when control comes back, I know exactly where I am because I just pick up where I left off. So I can rely on the stack and the variables in the stack to encode my state. I don't have to sort of build an object and stick them in there. A couple other points about iterators. We had a really nice implementation for them because what we did is we took the body of the for loop, turned it into a little procedure. The compiler did this, passed it in as an argument, and then every time the iterator wanted to yield, it just called that procedure. So it was a very simple-minded, very efficient implementation. And the final point is there was a loss of expressive power here because generators allow you to do more than what I'm describing. With generators, you could walk over two trees and check the fringes of the trees, sort of walking on them in parallel, where iterators don't support that kind of parallel. They're not full coroutines, they're partial coroutines. Okay, so that's all I want to talk about to Clue. I'm not going to explain exception handling. What we ended up with was what's more or less what you're familiar with today. And I just want to point out that we didn't just have data abstraction. We had procedural abstraction, we had iteration abstraction. So we had three main abstraction mechanisms, all of which could be polymorphic. So we had this sort of nice orthogonal design. Okay, so now it's about 1970. And depending on the time available, I think I'm going to skip this. I'm just going to say that I did continue to work on problems related to modularity. In particular, how do you design modular programs now that we have abstract data types to work with as well as procedures, and how do you reason about the correctness of them? But given the type that we're short in time, I'm going to skip these. Okay, and I'm going to talk a little bit about how we finally ended up with object-oriented programming. So I was developing CLUE. Bill and Mary were working on Alphard. That was the abstract data type. And although I didn't tell you about how we wrote specifications and stuff like that, all of this work was very much focused on semantics, interfaces, separate reasoning. It was very focused on the programming methodology goals. The work on Smalltalk was different. They had this inheritance mechanism, and they really liked the idea that I could write the code for something, and then I could write a subclass of that and add a little extra stuff, and I would get more. And, it's kind of an appealing idea. For example, if I have a set implementation, and what I want to get next is a set where I track the minimal element, or I track how many odd elements there are in the set, well, I can take my implementation of set, add an extra instance variable to remember whatever information I have to remember, add maybe a couple extra methods, change a couple of methods, and now I have this thing that's does a little bit more. So that was what they were really interested in with inheritance. What happened was I was asked to give a keynote talk at Uppsala in 1987, and this kind of spurred me to go and look at that whole other area of research that I had not been paying much attention to. And what I discovered was that, in fact, these inheritance mechanisms were used for two different purposes. One of them was the implementation that I just described, where I could get a set with even elements from a set. The other one was a notion of type hierarchy, a notion of families of types, where somehow many types were all members of the same family. Now, my personal belief is implementation's not all that interesting, the implementation use, but I thought the type hierarchy use was interesting. And I discovered, by reading the papers in the literature, that people were very confused about what this meant. For example, I read a paper that said that stacks and queues are each subtypes of one another. And by which they meant, you could use them interchangeably in a program that needed one or the other. But if you start to think about that, you can see that that's not true. Because if I write a program that expects a LIFO behavior, and I've passed something that has a FIFO behavior, this could really make a difference to how my program runs. So they weren't really thinking about it from the point of view of what is the meaning of things. So I was coming from a world where we thought a lot about the meaning of things, and this was a different world where they were thinking more about how do I write programs quickly by extending implementations that already existed, except they'd begun to realize that the types were related somehow, and so they had this notion of type hierarchy they were trying to sort out. So what I did was I invented what came to be called the Liskov substitution principle, and I talked about this in my keynote in 1987. This was Uppsala. And this was what I said in that paper. Objects of subtypes should behave like those of supertypes if used via supertype methods. So it's a very straightforward definition. It doesn't mean the subtype can't do more. It just means that if you expect the supertype and you're past an object of the subtype, you're not going to have any surprises. It'll behave just like you expect it to do based on the subtype specification. So it's very specification oriented. I have something I expect, I know a specification for it. I don't mind if I get something else, provided, as far as I'm concerned, the specification I rely on is still honored. Okay, so that was that. All right, now what happened after this was that the worlds merged, sort of. And around about 1990, Java appeared. So this was sort of the first time in which this work got into the mainstream. And Java is an object-oriented language. It has inheritance, but of course it also has type hierarchy. They separated out the mechanisms. And there is at least lip service to the idea that when you're talking about type hierarchy, you ought to get your semantics straight. And that's kind of where we are today. So what I'm going to do now is finish up by talking about sort of where we are today. First of all, modularity based on abstraction is the way that we design programs today. And it's amazing what we actually design. In fact, the internet's amazing. I didn't foresee this. I don't know if anybody really did. That sometime in the 90s, all of a sudden, the internet changed from something a few computer scientists were communicating on to something that pervades our life to the extent that I really think we've had a revolution akin to the Industrial Revolution. Our lives are just really different now, and they're continuing to change in ways that none of us foresaw. And that revolution, of course, is fueled by very sophisticated programs that, I've lost my screen, that work a surprisingly large amount of the time. And it's because people understand today how you develop big programs. And of course, another thing that's happened is as we've developed components of programs like databases and file systems, we reuse big components, but these, of course, are just the kinds of modules that data abstraction is talking about. Okay, so here's how I see the landscape. This is not a total landscape of programming languages, but this is what I think about. We have languages for experts. You can build big systems in these languages. Java, C#. The problem is, what happens if you want to teach Programming 1A? Okay, I mean the first programming course. These languages are really complicated. And there's so much cruft in them that in order to get to write that little program that says hello world, you know, the student has to sort of contend with all this other stuff that's going on in those languages. Partly this is because of what appeared to be a religious point of view, that if you had objects, you should not have procedures. You know, why? And I think that's ridiculous. I mean, data abstraction is very useful, but, you know, a sort routine isn't an operation of an array. You know, it's a separate thing in its own right. So procedures are very useful abstractions, too. So partly that's the problem. You couldn't write a little procedure that says hello world. You had to embed it all in this complicated class structure. Okay, so what do people do with Programming 1A? Well, what we did at MIT, and what I hear people talking about a lot, is we take a language that in some sense makes the first programming experience very nice. So we happen to use Python, you might use Ruby, you know, there's a few candidates. I know you use ML here, and I'm not complaining about ML, it's just that, you know, Java wasn't really what you wanted, okay?
We use Java for this.
You use Java, so you're still, I mean, all right. And we used to use Scheme, remember? I mean, that used to be the MIT way. Anyway, today we use Python. And Python is really nice to get started in. You know, it's nice. It has, you don't have declarations. It uses dynamic typing. It's got a huge, rich library. You can write procedures. You know, it's interactive and so forth. But the trouble is, you know, just get a little further down the path, and what you discover is they threw out modularity. They got no support for modularity. And, you know, this doesn't matter too much for when you're writing programs just for yourself. But if you think about writing programs in teams of programmers, you see what happens is the students in these classes, if they're going to learn how to write programs right, it's going to be because the instructor goes against what the language provides and says, oh yeah, Python lets you do that, but you shouldn't do it. That's bad. You have to do it this other way. This is not great. And in fact, it probably often isn't taught as well. And not only that, but students, you know, pick up these languages and they go on and they start to build big programs with them. And that's not good either. So, my dream, couldn't we have a program that's good for both novices and experts? You know, so we start them off simply, but we don't throw encapsulation out the window. Now, I've thought quite a bit about this, and it's not an easy design problem. And I just wrote up here all the things you would have to think about. So, you know, there's ease of use versus expressive power. When you build big programs, you need expressive power. There's readability versus writability. Python is very aimed at writability. The truth is readability matters a lot more for big programs because programs are read many more times than they're written. Modular encapsulation are for sure. We need powerful abstraction mechanisms. We need polymorphism and generics. And then a final point is state matters. You know, programs are basically about manipulating state in order to accomplish whatever the job is at hand. And so, although immutability is very important, so is state. And I think that you have to design your programming language so that you accept that and don't push the state over into some small corner of the language. Rather, think of ways that you can support immutability while still giving state the sort of first-class place it belongs in. Okay. The other challenge, I think that's a big challenge. I'd love to see somebody take that on. The other challenge is concurrency. Here we are in the age of multi-core machines. The big issue there is actually methodological. We don't know how to write the programs that use those machines other than ones that have embarrassing parallelism in them. And people are very worried about this. There's a big community trying to work on this. What I wrote down here are, first of all, I've been working for years in the area of distributed systems. Somehow the concurrency problems are less there, and I think it's because we use a kind of modular approach to concurrency. We tend to think in terms of the big units that reside at different places in the network, and inside there might be a lot of concurrency, but there's no notion that on the outside you sort of control the concurrency on the inside. And that's really related to my last point on this bullet. I've seen some work going on in parallel computing where people are proposing, let's just provide a few highly concurrent data structures. That's where all your concurrency and synchronization comes from. And the rest of you can just, write programs that use those data structures. MapReduce is very interesting, but limited, I think, in the class of applications it supports. I'm not sure about transactional memory. I'm a big fan of transactions, so maybe there is some hope there. I don't know where this work is going. It's really, in fact, completely unclear whether we ever will be able to consume the multi-cores in the way that the hardware people would hope that we can. So I'm going to stop here. That's the end.
Barbara, thank you very much. I found the talk inspiring. First of all, just to answer your question, we teach Java to novices. We teach it functional abstraction first,
Yep.
and then we move on to do data abstraction. But my question is, what's the matter with CLU as a language for novices and experts? What's it missing?
Well, I think that's a very good question. And one of the things I meant to say in my talk was we've had a long time now to understand type hierarchy and inheritance and what they're really good for. And I think it's time to step back from that and think that through again.
Right. So, I came away saying, well, we're not going to teach that to novices.
Yeah.
So then I just want to teach CLU. So let's have a good, modern, fast CLU compiler.
Okay.
So that's it.
Good thought.
So, we use Java in those intro languages, and we teach them data abstraction
Yep.
and representation hiding and algorithms. And then they get to their senior year where they have their job interviews, and they say, the interviewers asked us about this thing called inheritance. What's that? And we say, better you not know. Right?
Yeah. Yeah. Right. I don't believe that was actually a question. There's people, yeah.
So all things considered, what would you consider the preferable language as things in now? Python or what?
What do I think is the best language right now?
Yeah, for the introductory program.
I don't think Python's a good language because I think that a language that doesn't support encapsulation is not a good language. I honestly don't think there is one. Maybe ML might be the best that's in existence today. But ML, I feel, has too much history in it, and there's too many mechanisms sort of floating around. That's why I think it might be good to design a new one. Java's 20 years old. It's probably time for us to rethink what should be a mainstream programming language given the knowledge we have today. So there's no particular language I recommend. I sympathize with where these languages came from because I feel that the programming language, the professional programming language community stopped paying attention to the needs of ordinary programmers. And what happened was people that weren't in that community then stepped in to sort of fill the void. And maybe this would be a good thing for serious programming language people to pick up again.
So when you say that Python doesn't have modules, do you mean that it doesn't have like typed interfaces for modules?
You're talking about Python again?
Yeah, because Python has classes, and it also has this idea of modules which allow both classes and procedures, which is the ideal that you described. You want both classes.
It doesn't have encapsulation. So nothing prevents any part of your program from starting to modify what the associated code. You don't protect the implementation.
Okay.
Okay, that's the thing I'm objecting to.
Okay.
Yeah. Mind you, Java has that too. And it just isn't quite so first class as it is in Python. There's something down here.
Oh,
yes.
Yeah, excuse me. You were talking about Python and CNRI. I happened to work with Guido van Rossum, and we put together the team when he came over from the Netherlands to stand up Python. And I remember him saying that he had started out with ABC, which was a children's language, to teach how to program. Mm-hmm. And now that Python is quite established and people quite like it, I wonder if Guido or some young Python programmer might not go back and revisit that and have an easier way for people to know how to program, say even for grade school kids. You were talking about novices versus those that are more advanced, to have an easier conceptual way of learning that eventually you could move on to other things. Has that come up, or?
Well, I guess I'm not, to design a good programming language, you have to be very sophisticated about what programming languages mean. So the fact that you're a Python programmer is probably not necessarily the right, background for developing the programming language. I think what's going on here is that when you start programming, and I'm honestly much more interested in, I'm not so interested in how children learn, I'm much more interested in how we train the people who are going to be the professionals of tomorrow, is you really want to start with computational thinking. And you want to focus on what does it mean to make a program do what it's supposed to do. And the complicated modern languages kind of get in your way. So, you described how you tame Java so that you can, and that's the approach you have to take. But then as you get more sophisticated, what you have to do to compute gets more and more complicated, and you just need to have some smooth transition that allows you to grow in that way. But I think somebody sophisticated about programming languages would be the best person to do that development.
One more question.
Okay, one more.
I wonder whether you have a comment on a user problem. I moderate an email list on Foundations of Mathematics, which lives at NYU, and it uses the email list manager Mailman, which happens to be written in Python. And it has the most annoying, irritating bug. Every now and then I'm doing a perfectly normal operation, and it tells me error number 305. And I go to the systems people at Courant, who are very cooperative, but then they can't duplicate the error. Is this something about the people who wrote Mailman, or is it something about Python, or whatever?
So it sounds to me like what you've fallen into is the non-determinism problem. Programs are difficult to write. Best we can do with programming languages is to try and keep it as well under control as we can. That does not guarantee correctness. And when you throw into the mix concurrency, which I'm sure is in I'm not familiar with your system, but I'm sure it's in there might even be distribution, then there's lots of things that can go wrong. And if they go wrong because a particular sequence of events happened in just this way this time, then what you end up with is, first of all, those errors are very hard to cause during debugging because it has to do with a random sequencing of events. And secondly, they're almost impossible to cause to happen after the fact because it was just a non-deterministic collection of things that happened. You can't repeat it. So it's not Python. I mean, it might be Python because it might be there's some errors there too, but it's not really Python. It has to do with the the world that we live in today, non-determinism, the way that you can help these problems is to have much better platforms where there's a lot of stuff going on under the covers, where we're keeping track of what's going on as it's going on, so that if we need to find out the source of the error, we can go back and find it. And traditionally, those kinds of tools are turned off. They're often turned on while you're developing the program, and then they're turned off when the program gets into production. However, computers are getting so fast and powerful that perhaps, we are getting to a point where we don't have to turn them off anymore. And if they were on, you're actually complaining about two separate things. One of them is, who wants to hear error 305? That's terrible. But the more serious problem is, they can't reproduce the bug, and so they can't figure out what really went wrong. But if there were the right platform there, then you would be able to reproduce it, and it would be a much better way to keep the systems going forward.